Section 4.10, the Jordan Decomposition theorem. We have seen examples before where a matrix was not diagonalizable, but almost diagonalizable. So we had these cases where we had diagonal entry with 2's, for example, and we have seen that 2 is an eigenvalue, and we couldn't diagonalize the matrix. We couldn't get rid of these 1's in the superdiagonal. And we had example for a 2x2 matrix and even 3x3 matrix similarly. So it turns out that these structures are common for these matrices, especially these ones in the superdiagonal. And these are called Jordan decompositions when we get matrices like that. And these are more general than diagonalizations. The main theorem, the Jordan decomposition theorem, is this one. If A is a n by n complex matrix, and suppose that A has exactly k distinct eigenvalues, lambda 1, lambda k, in the complex plane, with geometric multiplicities gamma 1, gamma k, and algebraic multiplicities alpha 1, alpha k, respectively, then there exists an invertible matrix U, complex n by n, such that A times U equals U times J, or you can rearrange it to get A equals to U, J, U inverse, or you can also rearrange this to get J equals to U inverse AU, where J is a block diagonal matrix, which means that it's diagonal with the matrices in the diagonal entries, B lambda 1, B lambda k. So each block corresponds to different eigenvalues. And then B lambda j block is an alpha j block diagonal matrix, where alpha is the algebraic multiplicity. And it's still not diagonal matrix, it's block diagonal, which is built out of gamma of j, which is the geometric multiplicity of the eigenvalue, so-called Jordan cells, C lambda j mu ij, complex mu ij matrix. And these Jordan cells have this form that lambda j is in the diagonal, and in the super diagonal you have 1's and 0 everywhere else. So lambda j denotes the diagonal entries, the eigenvalue, so we can write this also as lambda j times the identity matrix, which gives you the diagonal matrix part, and then C0 mu ij. If we replace the lambda with 0, then we get 0 diagonal entries, and then this actually denotes just this one super diagonal part. So adding together the diagonal matrix with lambda j in the diagonal plus the super diagonal part, you get the whole matrix. And this goes, as j goes from 1 through k distinct eigenvalues, and also I index goes from 1 through gamma j, the geometric multiplicity of the lambda k eigenvalue. The number of Jordan cells in this block matrix, B lambda j, with size mu greater than or equal to L, is equal to the dimension of the null space of A minus lambda j I to the L minus the dimension of the null space of A minus lambda j I to the L minus 1, as L goes from 2 to all the way up to alpha j. The columns of U are generalized eigenvectors of the matrix A. We will talk about this later. And we also have that alpha, or A minus lambda 1 I to the alpha 1, A minus lambda k I to the alpha k equals to the 0 matrix. And we also have that if we denote with mu j, the smallest mu, such that the dimension of the null space of A minus lambda j to the mu equals to the dimension of the null space of A minus lambda j I to the n, then this mu j is less than or equal to alpha j for all j going from 1 through k. And we also have for these mu j's that a minus lambda 1 I to the mu 1 a minus lambda k I mu k equals to 0. The proof of this theorem is in chapter 1. As you see, it's a big theorem. It talks about the structure of the Jordan decomposition. Here is an example for one possible configuration for a block diagonal matrix where that belongs to just one eigenvalue, lambda 1, and it has several Jordan blocks. Actually, it's Jordan cells, really, the small ones. So here is a Jordan cell. The whole matrix has lambda 1 in the diagonals, but then what you see is that this super diagonal doesn't go all the way. Sometimes it gets interrupted. So these interruptions of ones denote the end of a Jordan cell and the start of another one. So this is a 5 by 5, this is a 4 by 4, this is a 2 by 2. Each have ones in the super diagonal. And then the one by ones, of course, there is no place for a super diagonal, so that you don't see ones there because these are 1 by 1 blocks. Jordan blocks play a very important role in modern control theory. These are mostly used in theoretical calculations, but of course theory is very important. So in modern control theory, linear differential equations represents systems, and then the eigenvalues indicate stability or instability in the system. And by control, the goal is usually to place the eigenvalues so that the resulting system is stable. That usually means that we want eigenvalue to have a negative real part. So we're not going to work with this, but since this is so important, we're going to go through two examples in the next section about Jordan decomposition examples. The first example, find the Jordan decomposition of the following matrix. The blocks should be ordered increasingly by eigenvalue and then by block size. Here's the matrix, 4 by 4 matrix. This order of the blocks is kind of artificial. Web work requires it for checking the solution. So the solution, 4 by 4 matrix, a lot of numbers already, a lot of things to calculate. You are strongly encouraged to check your answer using MATLAB command. First of all, there is a MATLAB command to calculate the Jordan decomposition. It gives you the U matrix and the J matrix for initial A matrix. And still, so you can check your answer with this command, but even during calculation, you should use MATLAB to calculate basic operations that we will need and that we already did in the previous sections. So for example, you have to calculate powers of matrices, that means product. Then we have to use upper echelon form, but the matrix for the MATLAB, the command is reduced echelon form, so it's a unique matrix that we get. RREF is the command. And for eigenvectors, let me remind you that eigenvectors are the basis vectors in the null space of A minus lambda I. So we also have a null space calculation command for MATLAB. This R part is also important in order to get nice integer or at least simple fractions for the vector elements. So first of all, we have to calculate the eigenvalues. We form this A minus lambda I. Still, you are not allowed to use determinants, but even if you want to use determinants, you get a 4-degree polynomial equation, and good luck solving that other than guessing. So if you want to follow the way we calculated eigenvalues before, Notice that this matrix has this special structure. The third column has only one non-zero entry, and that's actually the 3-3 entry here, which means that when you subtract lambda from the diagonal entries, you get 1 minus lambda here. And that means that if lambda is 1, then this whole column will be 0. Then if you do row reduction, elementary row operations, these zeros will never change. When you multiply and add rows, you are multiplying zeros and adding zeros. And that means that there will be no pivot in this column. So at the end, you will have definitely less than 4 pivots, because at least in this column, you're not going to have a pivot. So that means that lambda 1 is an eigenvalue. And then what we do is we now form the generalized eigenvectors. The theorem says that the U matrix in the Jordan decomposition is formed from the generalized eigenvectors of matrix A. Now the generalized eigenvectors are from the eigenvectors corresponding to powers of this A minus lambda I. So for that, first of all, we start with we need different powers. We also need different powers because in the theorem, we get the number of Jordan cells from the dimension of the null spaces of the different powers of A minus lambda I. So we need this for several purposes, for calculating the number of blocks, number of cells, and also calculate the generalized eigenvectors. So the first one, L, is 1. That means we just have A minus 1i. So one way to calculate this, let me actually start calculating using MATLAB. We have, let's create A, 1, minus 3, 0, minus 3, minus 9, 8, 0, 10. Next row, minus 9, 13, 1, 16, and 9, minus 10, 0, minus 12. Make sure that you entered it correctly. Maybe also let's calculate immediately the Jordan decomposition, which is useful to see what we're supposed to get. Doesn't look very nice. Did I do this correctly? Let me check again. And no, I didn't. If you look at it, the fourth 3 entry is supposed to be 0. I already mistyped it. So we can go back, and 4 and 3 entry, this should be 0. Let's try again. You can use the up arrow to go back to the previous command and calculate, do the calculation again. So this is the Jordan decomposition. Note that this is not what we exactly need, because we have to order the blocks increasingly by eigenvalue and then block size. We do have one of the eigenvalues, lambda 1, so that's correct. In the diagonal entries, we're supposed to have eigenvalues. You see that we're going to have another eigenvalue, minus 2. And here are the U vectors. Not very nice, because these are not integers, some of these generalized eigenvectors in the U matrix. So anyway, if we have A and we want to calculate A minus 1 times I, let me denote it with AL, A lambda. So the way you can calculate it is that you have to subtract 1 times the identity matrix of size 4 by 4 is in MATLAB is I4. So this is this matrix, A minus 1i. And then we can calculate the reduced row echelon form of this. Not A, the A minus lambda. And, well, I didn't calculate it exactly that way. If you multiply this with 3, the first row, you get 3, 0, 0, minus 1. So we don't want to use decimal numbers usually. And we are allowed in the calculation, we are allowed to multiply a row, the whole row with a number. That's one of the elementary row operations. And this is one upper echelon form, this is another upper echelon form. This is reduced row echelon form because all the leading entries are 1. This is just one upper echelon form. It doesn't have to have 1 in the diagonal entry. So to calculate the null space of this, the null space of A minus lambda, and it should be rational with relatively nice numbers, we get 0, 0, 1, and then if you multiply this with 3, you get 1, minus 3, 0, 3. Order doesn't matter in this case. So we get 2 linearly independent vectors. That means the dimension of this null space is 2. Then we need the second power. So that's AL times AL, or yeah, that should be all lowercase, the L. Also AL squared should give you the same answer. So we get another matrix, and then we reduce this to get the reduced row echelon form, and possibly this is where we get the null space. What you can see is that the reduced row echelon form is the same as before, and hence the null space will be also the same as before. And that means the dimension is the same. So once you have the same dimension as in the previous step, we don't have to continue, because what the theorem says is that we have blocks of size at least 1 by 1, which equals to the dimension of A minus lambda I to the 1, and that's 2. And the blocks of size at least 2 is the dimension of the square of A minus lambda I minus the dimension, that one is missing here, of the null space of A minus lambda I, the previous one. Let me go back to the theorem and point this out. So mu, the size is at least L. You get this number, how many Jordan cells you have, by subtracting the dimension of the null space of the nth power. From this, the dimension of the null space of the L minus first power. So we get 2 minus 2, which means we don't have blocks of size at least 2 by 2. We only have blocks of size 1. And also notice that the theorem says at least. So from the subtracting the 2, we get exactly one size. With lambda equals 1, we have 2 blocks. That means we have a 1 by 1 block and another 1 by 1 block. And there is no super diagonal entry, because that would create a 2 by 2 block together. So 2 1 by 1 blocks, which means it's a diagonal part. We will also need the corresponding generalized eigenvectors. In this case, these are just the regular eigenvectors. The order doesn't matter. So we need more eigenvalues. We found only one so far. It has multiplicity 2. We need more eigenvalues, so we have to return to this matrix when lambda is not 1. So we already worked with this kind of matrices. It's kind of painful. It's better to actually work with numbers than these expressions 1 minus lambda. So for that reason, one idea would be to interchange row 1 and row 2, and then use this first row, which was the previous fourth row, then use this as a pivot. And then to add this to the second row and add to the third row will make these minus 9s go away. For the fourth row, we would take the common multiple of 9 and 1 minus lambda. So we would need minus 9 times row 4 plus 1 minus lambda times row 1. And this is the case when lambda is not 1, so we don't have to worry about multiplying with 0. So then what we get is we get these zeroed out. Make sure that you do the calculation correctly. So this term is also zeroed out. Then minus 9 times row 4, you get 27. Then 1 minus lambda times minus 10, so it's minus 10 times 1 minus lambda. These zeros don't change. Then we have another 27, minus 3 times minus 9, 27, and minus 12 minus lambda, which is minus 12 plus lambda times 1 minus lambda. You should check carefully in each step what matrix you get. Because, for example, the same way as we saw that we get an eigenvalue because we get a completely zero column that cannot have a pivot there, you can also notice here that you get a completely zero row if lambda equals to minus 2, because then minus 2 minus minus 2 is minus 2 plus 2 is 0. And that means that we get another pivotless row. So that means that lambda equals minus 2 is an eigenvalue. We check what the multiplicity is, and at the same time we calculate the generalized eigenvectors by first calculating a minus lambda I, which is a plus 2i. Let me do that in MATLAB. So a plus 2 I of size 4. Sorry, this is now the new a minus lambda, and it's a plus. So this is the first case. And then, by the way, we have al squared for the second matrix. Then we reduce both of these. We get, well, I wrote here 3, but of course we can divide it by 1 in order to get even better number there. So make sure that this is correct. And then you can check what the null space is if you calculate here, or you can just use the null space calculation from MATLAB. Make sure that you use the rational version of that and not a, but al, a minus lambda I is what we need. It's 0 minus 1 minus 1, 1. So the dimension of this is 1. Then we also calculate the reduced row echelon form of al squared and the null space of this new al squared matrix. And the dimension of this is 2. So what the theorem says is that we have Jordan blocks of size at least 1 by 1. We have one of them. So we have Jordan blocks of size at least 2 by 2. That's the dimension of the null space of a minus lambda I squared minus the dimension of the null space of a minus lambda I to the 1. So it's 2 minus 1, which is 1. So we have Jordan block of size at least 2 by 2, one of them. And the 2 by 2 Jordan block with eigenvalue minus 2 has this form. Because we have a 4 by 4 matrix and we already have a 2 block, we don't have to continue and calculate a plus 2i to the third, because we cannot have a larger block. So 2 blocks already give you a 4 by 4 matrix. Generalized eigenvectors. So we need 2 vectors, and as you see, we don't get 2 vectors from the regular eigenvectors. So The way to get the generalized eigenvectors, they're supposed to form a Jordan chain. So choose one of the two vectors from a minus lambda I square, like v1 equals to the first one, minus 1, 1, 0, and multiply this with a minus lambda I to get another vector. Incidentally, you see that you get actually the eigenvector. And very important also that you have to list these in reverse order. So first what you calculate and then the other vector. So these are generalized eigenvectors, and these actually form, this is a Jordan chain. From a previous section we considered Jordan chains. Then a Jordan form is when you put together these Jordan blocks in the diagonals, as blocks in the diagonal. So this was the first one that we calculated, then the second one, the 2 by 2, 2 1 by 1, and the 2 by 2. Very important, web work needs it ordered increasingly by eigenvalue and then by block size. So first we need this block with the minus 2 eigenvalues and then the 1 eigenvalues, because these numbers are larger. The block size right now it doesn't matter because you have one block, and this has to be first anyway. So then U, in web work this is denoted by P, the U matrix. Make sure you order the generalized eigenvectors according to the Jordan blocks. Even then it's not determined uniquely, but this is fine. So what we have is that the first Jordan block minus 2 diagonals that has these vectors, generalized vectors. So they are the first one in the U. And then the eigenvectors corresponding to 1 that we calculated before. These are just regular eigenvectors and the order doesn't matter here. That's why it's not unique, but it turns out that both orders should work out. On the other hand, when you calculate the generalized eigenvectors in the Jordan chain, then the order matters. Very important, otherwise it doesn't come out correctly. So we have the Jordan decomposition with the U matrix and the J matrix. You should check, of course, in MATLAB that this is really the case, what you get. Well, notice that in MATLAB, the command Jordan doesn't give you the same order. It's kind of a random order. Why would you have one first and then also last in the middle of the two blocks? At least I don't know what the theory about this ordering. So this is not what we need. Let's create a J1 matrix with what we calculated. 0, 0, 1, 0, and 0, 0, 0, 1. So this is the J1 matrix we calculated, increasing order of eigenvalues. And the U1 matrix, 0, minus 1, 1, 0, minus 1, minus 1, minus 3, 0, minus 1, 1, 0, 1, 1, 0, 3, 0. And then we can calculate and compare this to the A matrix, what you get if you have U1 times J1 times the inverse of U1. Notice that there are some rounding errors, so for that reason you might see some zeros here, which suggests that it's not exactly an integer, but if you ignore those, we get the exact answer. Next example, also a 4 by 4 matrix. We want to calculate the Jordan decomposition of this matrix. Again, the Jordan block should be upper triangular. Note that some books actually use lower triangular Jordan blocks. And also the blocks should be ordered increasingly by eigenvalue and then by block size. Not a general requirement, but WebWork checks it this way. And again, it's useful to see what we're supposed to get in advance. So let me enter A. Make sure that you enter it correctly. And then let's calculate the Jordan decomposition. So it shows that we're gonna have -4 eigenvalue and -1. You can also see that we have 2 Jordan blocks corresponding -4. This is a 2x2 Jordan block. This is a 1x1 Jordan block. And we have another 1x1 Jordan block for the other eigenvalue. So let's see how the calculation goes. To get the eigenvalues, we form this A minus lambda I. Again, let's find some easy way to get an eigenvalue. Notice that we have a column with possibility to have a completely zero column if lambda equals to -4. And by the way, then not just the second column, but also the third row is completely zero if you get if you substitute lambda equals -4. So lambda equals -4 is definitely an eigenvalue, because then in these columns and rows we're not going to have pivot. So let's see what the eigenvectors are. If you want to do it the long way, I started doing it actually by hand to form A minus lambda, where lambda is -4, it becomes A plus 4i. So you add 4 to the diagonals to get 6, 0, 0, and -3. And then to get the reduced row echelon form, we already have a completely zero row. We get another zero row if you add the first row to the last row. You can also divide the first row by 3 to get better numbers, and then form 2 row 2 minus 13 row 1. And finally we get this, and then we get from here 2 eigenvectors. But anyway, this is a long calculation, so it's better to form this table, which means that we form A plus 4i. So we have A plus 4 times I of size 4 by 4. Then if you want to check what the reduced row echelon form, let me denote this previous matrix with A lambda or AL, since it's A minus lambda. Then the reduced row echelon form of A lambda, AL, and the null space with rational vectors. So this is 0, 1, 0, 0, minus 1, 0, minus 1, 1. It has dimension 2. Then we need the square of this. A minus lambda I square. We get null space that has dimension 3 now, and in order to have no fractions, we can multiply this second one with 2 to get 1, 2, and the third one by 2 to get -1, 2 in the first and last entries. So the dimension is 3. Now theoretically we could have even higher dimension if we have repeated 4 times. So we do have to check what the null space of the cube is. It turns out that this is the same. The dimension doesn't change. So according to the theorem, first of all, the algebraic multiplicity is 3. And for the Jordan blocks, what we have is of size at least 1 by 1. That's the dimension of the original one, so we have 2 of those. And of size at least 2 by 2, the dimension of the null space of a plus 4i square minus the dimension of the null space of a plus 4i is 3 minus 2, which is 1. So that means that we have at least 1. Now we have 1 at least 2 by 2. And then we also have, by the way, that at least 3 by 3 if we don't have any. So for that, what we need is the dimension of the cube minus the dimension of the square, which is 3 minus 3, 0. So we don't have 3 by 3, we only have 1 2 by 2. And since we have at least 2 of these blocks, we have other option that we also have a 1 by 1. So we have a 2 by 2 block, at least one, and then we don't have exactly one, I'm sorry, at least 2 by 2, exactly one. We don't have 3 by 3, and then since we have at least 2, I'm sorry, we have exactly 2, at least 1 by 1, and we already have 1 2 by 2, then we are left with 1 1 by 1. So the difference of these numbers, 2 minus 1, gives you the number of the 1 by 1 blocks. So that means that this is how it's supposed to look like. Also note the requirement as that it's supposed to go in increasing size. So first the 1 by 1 and then the 2 by 2 block. The corresponding columns of U are generalized eigenvectors. We have to start with the largest power, where we have something different from before. So that's the square, a plus 4i square. And one of the 3 eigenvectors is, for example, 0 1 0 0. It's also an eigenvector. Notice that. So that means this is not good. The definition of a generalized eigenvector is that it's in the null space of this power, but not in the previous power's null space. Then from the other two, you can choose any of them to form a Jordan chain. Let's choose this one, 1 0 2 0. And then the Jordan chain second vector is that you multiply this vector from the left with a plus 4i. And incidentally, you get actually this other vector. So the corresponding, this correspond to the 2 by 2 Jordan block. And we had to add these two vectors, again in reverse order, plus the vector from the a plus 4i that is linearly independent. So this 0 1 0 0 is already there, so we cannot choose this one, but we have to choose then the other eigenvector. So these two vectors correspond to the 2 by 2 Jordan blocks because they come from the Jordan chain with 2 vector. And then the column corresponding to this is from the eigenvectors, which is not linearly dependent from these others. So that means it must be this, because this is already there. And the order is important. So first we start with the one corresponding to the 1 block, and then the Jordan chain. And also here the order is important, that this, but that you calculate with the matrix multiplication, supposed to be the first one, and then the second one. So we are missing one eigenvalue. We're supposed to have a 4 by 4 matrix. And you can also see that this eigenvalue will have multiplicity 1. We need a second eigenvalue which doesn't equal to -4, so we have to go back to this A minus lambda I matrix. So if lambda is not -4, that means this is not 0, it's a non-zero number, we can scale this then to get 1. So that's helpful to get a nice number 1 there. what we can also do is then with this 1 in this third row, we can cancel things under and above it by multiplying this row and adding multiples of this row to the previous 2 rows and to the fourth row. So we can zero out these entries. That's helpful. But eventually somehow you have to do at least one step of row reduction. Here what I did is I used the first row to cancel out this -6 in the fourth row. And the reason I did this instead of working with the second and the third row is because we only have 2 non-zero entries. So if we cancel this entry, then these zeros will not change. And then we end up with this row here with only one entry, which is then questionable to be 0 or not. So from here we can calculate another eigenvalue. To cancel -6, we multiply this with 2 minus lambda and add 6 times the first row to this. So we get 0, 0, these zeros don't change and this becomes 0. And then here we get 2 minus lambda multiplying -7 minus lambda plus 6 times 3, 18. So we have less than 4 pivots. We have an eigenvalue if we have less than 4 pivots, which means if this entry is 0. So we calculate what this entry is, we multiply this out, and then we go back and simplify and factor it. And we get that lambda equals -4 is one possibility, but this is not a new eigenvalue, we don't care about it. The other possibility is lambda equals -1. And again, we don't have to check lambda equals 2 because we cannot have more eigenvalues. So we already have -4 with multiplicity 3, we have -1 with at least multiplicity 1, and we cannot have more multiplicity because we have to have 4 by 4 matrix. And that also means that we cannot have more eigenvalues. So then the corresponding eigenvector, since the multiplicity is 1 here, it will be calculated with a minus lambda I, which is a plus 1 I. Again, you can use MATLAB to calculate this. Otherwise, it's a lot of calculation, then it's easy to make mistake. So A is the original matrix, and we need A plus 1 times I of size 4 by 4. Then we need the null space of this. And we get -1, -2, 0, 1. So then we have the Jordan block with the previous Jordan block, and now we have -1, and the order is correct because -1 is larger than -4. So the blocks are ordered by increasing eigenvalue, and also here they are ordered by increasing size. So 1 by 1 and then 2 by 2. Make sure the corresponding eigenvectors are in the same order. First, this 1 by 1 block, then the 2 by 2 blocks, Jordan chain vectors, and then finally the eigenvector of -1. And again, it's useful to check that this is really correct because A equals to U times J U inverse. So based on these two examples, we covered different cases. One where we had two Jordan blocks of size 1 by 1 and the Jordan blocks of size 2 by 2. And here we had here also we had two Jordan blocks of size 1 by 1, but corresponding to different eigenvalues, and a Jordan block of size 2 by 2.